What's up, geometry students? We're going to talk about dilations, about a center point. We're going to just be a little more exact instead of just like seeing pictures and saying, how much bigger is this one compared to the other? It's like create something this many times the size is the first thing. And what we're going to focus on is having kind of a center point. I call it like a superhero. And this superhero will take points around it and it will just like push it away from where it's located in the same direction, following the same slope of the line. So this being called the center of dilation is the most important point. I call it like the superhero. I like to list it off. Maybe this is the point 2, 3. Maybe this is the point 5, 5, 4 or something like that. And let's say this is a point P. And we want to push this 0.54 away from 2, 3. Well, like how far away? Well, just pushing it back to itself would be called the dilation of like times 1. I call this a scale factor. So if I just take the point P, kind of pull it towards C and then push it right back to point P, it ends up where it started, we say that we've scale factored it by a factor of 1. It kind of goes back to where it was. If I want to push it out twice as far, well, we would just like continue to follow the slope, meaning this would go to 0.8 and 5. That would be like twice as far. But what's really important is understanding it doesn't matter how far you want. Maybe we want it to be like 7 times as far or half the distance. All you would do is take this slope and like keep the ratios intact. So if plus 3 plus 1 is a scale factor of 1, plus 21 from C, which gives you to 23, plus 7 from 3, which gives you a y coordinate of 10, this would be your new point. And this is the idea of your hero pushing points away. Now, he pushes points away. How can we figure out where he's located? Well, the key is he like pushes it directly out from where he's located. If we connect points that we see that are dilations of each other, we can see that where they intersect, if it works out, if you have a straight edge, use your straight edge. See if I can do that again. Yeah, great. We can see this point right here would be the hero. Maybe we'll call it H for the hero. The center of dilation. And maybe it took this point E and then brought it in half as close, kind of pulled it in using its powers. D moved it in half as far. C moved it in half as far. Half as far. Let's say H is at the point 4, 1. I'm just going to make up numbers just so we're comfortable with this. Let's say H is at the 4, 1. Let's say C is at the point 8, -2. Well, a scale factor of 1 would have added 4 and subtracted 3. If I want to do a scale factor of a half, I would take this 4 and multiply by a half and say, oh, take 4 and add 2 to it, or like find the midpoint kind of thing. Instead of -3 and minus a half, 1.5 to be -0.5. So like we would say if this was 8, -2, this would be 6, -0.5. That's not really what it's asking you, but I'm just like assigning points to it. You can see it's the same thing here. Like A must be our hero, must be our center of dilation. This is the important point that is pushing your points away from you in the same direction that's kind of you're pointing in. You could say this is B, this is C, and then you're pushing it farther to get B prime and C prime. Or just like this one, you could kind of pull it in and have the primes in different locations. So we would say that A is the center of dilation, it's the hero. Superhero. Okay, what if we did not have coordinates? What if we just had a compass and a straight edge? Well, it's pretty easy to see, but then to find the exact values, a little bit more complicated. Oh, this is why, like, the computer's very slow right now. This is why. Oh, and then I just got rid of. Smart Notebook's really slow right now. There it is. All right, very slow. Cool. Well, we could use the straight line to be like, okay, here's my hero, here's my superhero, and he's using his telekinetic powers to push our points away from it. There would be one line. Cool. Here's another, then a third one. Cool. If we want to double things, this would be a scale factor of 1 to go back to where it's located. If we wanted to use a scale factor of 2, we'd want to double our lengths. So we just measure out our length and then double it. Cool. Move over, double our length. There we go. Double our length. There we go. I don't want the bar graph. All right. Now, what did we do? We just created these dilated points. A gets dilated to A prime. B gets dilated to B prime. C gets dilated to C prime. If we connected these 3 points, let's go ahead and do it with red. A prime to C prime to B prime, we can see this triangle is twice as big as this triangle. If we could measure, we would be able to see. Let's go back to this guy and see, like, let's look at this length here. C to B, here's C prime. To B prime. Double the length. Pretty cool. Okay, so just did that. This seems like all the lengths are the same, which means should be pretty straightforward to dilate all of these lengths if it's the same. Let's just double check. It looks like we have a center of a hexagon, pentagon. And we want to scale factor it by a half. So I want half the length. Are you guys looking for Mr. Dixon or somebody else? Okay. He is around. Just all right. So the idea is we want to push these points away or pull them towards us because C is the superhero who has the telekinetic powers. Cool. Let's figure out the lengths using our friend. Okay. All right. So let's see. Maybe I'm not exactly on the middle. I don't want to. I'm going to be honest, guys. I'm not going to do each one of these. I'm going to assume that they are pretty much dead. This point is dead in the middle, which means these lengths are all the same. I don't know why this happens. So if I need half the distance, what do I have to do? I have to create a bisector of at least one of them, and then I will keep that distance for all of them. So here is my bisector. It's half the distance. And now I'm just going to hold on to that half distance for the rest of my points. And almost just draw a circle around here. And be like, all of these are half. This pentagon will be half the size. If I take this length here and double it, essentially get that length there. All right, cool. Are the two figures similar? Explain how you know. Well, we can compare the sizes, make sure that they're all scaled the same way. So, example, from m prime to n prime, this is 1. From m to n, this is 2. Okay, so it looks like we want to show that this is twice as big as this. Well, let's look at the length of ON. Probably not a good length to do. I mean, I can go ahead right now and look at this thing, LM. It should be twice the size as L prime M prime, and it's not. How do I know? How do you find diagonal lengths? Well, use the Pythagorean theorem. L prime M prime is 2 squared plus 1 squared square rooted. So that's root 5. This is root 5 here. Well, this is root 5 as well. So no, not all sides are scaled. Cool. All right, well, we're going from the origin, so our superhero is located at 0, 0. This is the most important point. This is your superhero. We are dilating things by a factor of 2. All right, what I like to do is list off the points. So I have 0, 0 as our hero, and then I'll have negative 4, 2, point C. I got 0, 0 on the point negative 1, 1. And I got 0, 0 on the point 3, 4. Now, these are the easiest dilations about the origin. We're scaling by a factor of 2. So remember, if you're like subtracting 4 and adding 2, that is scale factor of a 1. If we want a scale factor of 2, we'll just take this plus 2 times 2, start from 0, add that. Take this minus 4 times 2, and it's minus 8. So it's very easy because you don't have to add it from 0. You're just applying the slope. You get negative 8, negative 8, 4. We'll get minus 2, positive 2, minus 1, plus 1, doubled, plus 3, plus 4, doubled. So A prime is negative 2, 2. B is 6, 8. Cool. So close, yet so very. We're going to different line segments. Very easy to dilate points if you just understood last unit and you understand how to use your table and understand your slopes and your x lengths and your y lengths. Find the length of A prime, B prime. Well, like we know it's going to be double the length of AB. We could find the length of AB. 1, 2, 3, 4, 1, 2, 3. So it's a 3 squared plus a 4 squared. AB squared is going to be square root of 25. AB is 5. This is going to be 10. I guarantee you. Now we can check. It's going to be a 6, 8, 10 triangle. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. Is that right? 1, 2, 3, 4, 5, 6. Yep. So this is 10. You could say 6 squared plus 8 squared equals A prime B prime squared. This is 100 equals A prime B prime squared. We're using the Pythagorean theorem. We get A is 10. Let's find this ratio C prime, A prime, and CA. So we have to find CA. This is 1, 2, 3, and 1. So this triangle is 3 and 1. 3 squared plus 1 squared equals CA squared. So this is 10 root 10. Cool. Guarantee you this is 2 root 10. You might not be sure. You might want to double check. A lot of people think that C prime A prime is going to be double this length, which is root 20, but that's not double the length. The answer is going to be 2 root 10, but we can double check. 1, 2, 3, 4, 5, 6. This length is 6. This length is 2. We double our x's and y lengths. This is 4. This is 36. It'll be root 40. And root 40 does simplify to be 2 root 10. So C prime A prime over CA is 2. Oh, what's that? Your scale factor. What about B, C, and B prime, C prime? Well, I'm just going to do it the easy way because I know, like, B prime, C prime, what its lengths are going to be if I know BC. So let me erase some stuff, that way you can see. BC is 1, 2, 3, 4, 5, 6, 7. This length is 7. This length is 2. I could have put the points on top of each other. BC, 3, 4, negative 4, 2, plus 7, minus 2. Okay, so 49, 50, 51, 52, 53. So BC is root 53. B prime, C prime will be 2 root 53, which gives us 1/2. That's showing you how BC is half the size as B prime, C prime. All right, we're not really dilating out of a different point. We're not really pushing from a different point, but pushing from different points isn't very hard. And we'll just practice it in class before we take a quiz on it. I mean, it's like fun to think about. Pushing things, either bringing it towards you or pushing away, being like a Jedi. You want to find the length of side AB? Well, here's A and here's B. I subtract 4, add 4. So I got A squared plus B squared equals C squared. So this is 32 equals C squared. C equals the square root of 32, which is root 16 root 2, which is 4 root 2. If the figure is dilated by a scale factor of half, the new AB, it's got to be 4 root 2 divided by 2. Well, that's actually 2 root 2. A lot of people might want to divide the 4 and the 2 by 2, but it's not going to be the case. Think about, what would you do if you have like 4 times 3, 4 times 6 divided by 2. 4 times 6 is 24. Divide that by 2. The answer is 12. Well, if you divide the 4 by the 2, you get 2 times 6. Okay, that's 12. If you try to divide both of these, you've actually divided by 4. You divide the top by 2 twice. So don't make that mistake. Use numbers to double check. We did not do any dilations around other points, but you'd be okay with that. And I hope you understand the superhero using its telekinetic powers to push away points or bring them back towards you. All right, peace.